Okay, recall we said that vector R was represented by a point on a curve in n dimensions. So if you reconsider the system x, y, and z, and any curve, parametric curve, where a point on the curve is in fact represented by the position vector. That is the vector that begins at the origin and has a terminal position on this curve. So vector R is what we say a function of of some variable t, parameter t. So this in 3 coordinates would be x, y, z, where each of the x, y, z's depend on the parameter t. At the point B, recall, we said that the tangent vector is given by the derivative of vector r, i.e. vector r dot, which recall was given by x dot, y dot, z dot. Dot being the derivative with respect to the parameter t in general. Now, what we're going to do is define so this r is a tangent vector. Recall we said that this vector r is a tangent at the point, so it's a tangent vector. The tangent vector is then the vector at the point P which is tangential to the curve. The unit tangent vector is the vector that is parallel to r dot. In other words, it's a vector at the point P, tangent vector, but with magnitude 1. So, the unit vector, unit tangent vector, specifically, is given by the vector r dot, your tangent vector, divided by its magnitude. So the magnitude of this vector is 1, and it's a tangent vector, and specifically the unit tangent vector. We now rewrite this unit tangent vector, or incidentally, we'll refer to this unit tangent vector as the vector u. So the vector u is the unit tangent vector. So at this point, we're going to rewrite many of these in terms of the arc length parameter. So we will now define as some arc length parameter in the following way. It will be given by the integral of your vector, your tangent vector, which is your vector r dot, magnitude integrated with respect to t. So the magnitude of r dot integrated with respect to t is going to be defined as some number s. It's an arc length parameter. As it stands there, it is a function of t. So once you've done your integration with respect to t, it's clear that this is a function of t. So this is also a function of t after you integrate with respect to t. From this it follows that ds dt is equal to the mod of r dot. Just differentiate both sides and it's clear what will happen. i.e., that is, your unit tangent vector, vector u, defined above, can be written in terms of this s in the following way. So recall that your unit tangent vector is the derivative of the vector r with respect to t. Sorry, that should be the derivative of the vector r with respect to t divided by the magnitude of that derivative with respect to t. This denominator is essentially just your magnitude of r dot. So now if you rewrite that slightly, this is the dr dt, where r is a vector, divided by the mod of r dot is ds dt. So this is ds dt. And if you use, let me just write that a bit better. That is s t. So it's dr dt divided by ds dt, and by a chain rule, this is then clear is dr ds. So s is exactly what it was above. So the unit tangent vector has two forms. The form given there as r dot over the mod of r dot, which is what we usually use to compute the unit tangent vector. But it's also given in this form down here. That's also another form of the unit tangent vector. Right. Now, we can use this parameter s to determine the length of arcs. So let's just go back again to what we had above. So if you have some curve in 3 dimensions, we said that this curve is given by vector r, that's x, y, z. And also, if you choose any point there, that is given by the vector r dot at any point. Now, if you were to choose 2 points on this curve, suppose t equal to alpha gives us that point, and t equal to beta gives us a second point further on. And suppose the curve is traveling in that direction. So this is, the first point is given by t equal to alpha, the second point is given by t equal to beta. That's called the first point P and the second point Q. So the distance along this curve PQ, along this curve vector r, between P and Q is called the arc length between alpha and beta. Okay? So, and that is given essentially by this integral involving s. So the arc length of the curve between points P and Q, arc length of PQ, is equal to the integral from alpha to beta. The direction here is important. The mod of the derivative of the vector r. So it's the mod of the vector r dot dt. That's the arc length. And you notice this is essentially your ds dt evaluated between alpha and beta. So just, we might emphasize that this is in fact your ds dt. ds dt was the general integral without the alpha and beta. This would be then ds dt evaluated between lower limit alpha and upper limit beta. Okay, let's do a simple example using the old helix. So, suppose we consider the helix. Remember, the helix, the circular helix, had a vector notation, a vector equation given by vector r equal to cosine t, sine t. This is the helix of radius 1. So this is, if that is your x, y, z coordinates, x, y, and z, this is your helix that does that. And this one is of radius 1. That was the equation of the helix. The vector r dot, the tangent vector at each point for this helix is given by the vector r dot. That's very simply differentiating each coordinate with respect to t. So that's minus sine t, cosine t. Sorry, that last coordinate should have been t. Please take note of that. So this is derivative 1. Right. The magnitude of vector r dot. That's very simply your usual magnitude of a vector. That is equal to the square root of minus sine squared plus cos squared plus 1. So that's minus sine squared, in brackets of course, plus cos t squared plus 1 squared. Take the square root of all of that and you end up with a number independent of t. That's purely coincidental. So this is the square root of 2. There we are. That's magnitude of vector r dot. So that, just for interest's sake, the unit tangent vector, which is what we call vector u, unit tangent vector, is actually vector r dot divided by the magnitude of vector r dot. So the unit tangent vector is equal to the vector r dot divided by the magnitude of vector r dot. Magnitude of vector r dot is just root 2, so this is 1 over the square root of 2 into minus sine t cos t1, like so. There we are. If you wanted the arc length of, say, just one circle, or what we call one twist of this helix, we have the following. So, let's get that right. So one twist of this helix, which is the helix we sketched there, is obtained between, say, t equal to 0 and 2 pi, is obtained by t equal to 0 up to t equal to 2 pi. That will give you something that does this. So it will do that. So maybe this point here is obtained by t equal to 0, that point there by t equal to 2 pi. So let's insert that as t equal to 0 gives you that point, and that final point is given by t equal to 2 pi. Like so. Let's write that a bit better. So that's obtained by t equal to 2 pi. Okay. And suppose we wanted the length of this complete twist. Right. So that essentially is the arc length. So this, the length of one twist, the length of this single twist, right, is essentially your arc length, and is given by the integral between t equal to 0 and t equal to 2 pi of mod of r dot itself, dt. We've done the mod of r dot early on. Very quickly, it's just a square root of 2. So this, in this context, is the integral from 0 to 2 pi, integrate square root of 2, that's the mod of r dot dt. So this is equal to the square root of 2, integrate 1, you get t, and then you integrate between 0 and 2 pi. Once you've integrated all that, the square bracket is 2 pi, so what you end up with is square root 2 pi, like so. We can do that, or do a similar kind of calculation where we take a modified helix. So this one is a helix with the spaces between each twist being the same. You can have an exponential increase between the various twists. Right. So in the second example, right, we have the modified helix. Now this is also an helix, it looks like a spring, but the z coordinate doesn't increase in equal spaces, but rather in some exponential way. So the modified helix is your vector r equal to, again, cosine t sine t, so that will give you a circle of radius 1 in the xy coordinates, but the third coordinate is not t, but rather e to the t. So what's happening is you've got this helix going like this. You've got this. So you see, it's the spaces between the various twists is increasing exponentially. And suppose we wanted the length of this between 2 points given by the following. So find so you find the length of this helix between 2 points. So this time the points are given in coordinates. Between the point with coordinates 1, 0, 1 and 1, 0 e to the 2 pi. 1, 0 e to the 2 pi. We need the t values that gives us the 2 points here. It's clear that this point here is obtained by t equal to 0. And this point is obtained by t equal to 2 pi. So when we do the length between these 2 points, we'll be integrating between t equal to 0 and t equal to 2 pi. Right, so the length. Let's just change that color. The length then is equal to the integral between 0 and 2 pi of always the mod of r dot dt. And the mod of r dot is the magnitude of the vector r dot. So where the r dot is given by the following vector. The vector r dot is the derivative of vector r, which is minus sine t cosine t e to the t. And the magnitude of this vector is the square root of the x squared y squared plus z squared. The x squared coordinate squared plus the y coordinate squared gives you sine squared plus cos squared, which is 1. And the z coordinate squared is e to the t squared, which is e to the 2t. Take the square root of all of that. That is the magnitude of r dot. Right, what we need now is the length of this curve r between t equal to 0 and t equal to 2 pi, given by that formula for the length up there. Right. Therefore, the length is equal to 0 to 2 pi, right? The square root of 1 plus e to the 2t integrated with respect to t. So this problem essentially is an integration problem. How to integrate this? So there's various ways to integrate this. I'm going to put u equal to this integrand, the thing to be integrated, and use some sort of substitution. So at this point then, I'm going to say let u equal 1 plus e to the 2t to the half. Therefore, u squared drops the square root, and u squared minus 1 ends up being e to the 2t. Essentially, we need to replace the dt also. So u squared is 1 plus e to the 2t. Take the 1 to the other side, you get u squared minus 1 is equal to e to the 2t. Right, using the chain rule, differentiating both sides with respect to t. Differentiate u squared with respect to t, you get du, you get 2u du dt. And the right hand side, you get 2 e to the 2t. And then cross multiply by dt. This is what you get. Right. So that therefore, okay, u over u squared minus 1. So let's, well, the 2's cancel off. Let me just show where this comes from. So u over e to the 2t equals dt. And you want the left-hand side all in terms of u. So therefore, we get u over e to the 2t is u squared minus 1. So that's u squared minus 1 equals dt. This comes from that step there. Okay? Right. So we're replacing in the integration of the length, in that integral there, the square root of 1 plus e to the 2t is u, and the dt will be replaced by what we have here. So therefore the length now becomes, so therefore the length of one twist, or the length of the curve between those 2 points is given by the integral of course, we need to change the limits. This is going to be u, that is replacing the square root, and the dt is u over u squared minus 1, integrated with respect to u now. This is substituting back. But in this integral, we need to replace the limits. The lower limit comes from t equal to 0. The upper limit comes from t equal to 2 pi, but that's in terms of t. So, since t is equal to 0 and t equal to 2 pi, we get the following. So t equal to 0 implies, in terms of u becomes, substituting back, u simply becomes the square root of 2. And if you put t equal to 2 pi, the value of u, which is going to be the upper limit, becomes the square root of 1 plus e to the 4 pi. So this is the square root of 1 plus e to the 2 times t, so it's 2 times 2 pi, which is 4 pi, like so. So the lower limit is square root of 2, the upper limit is square root of 1 plus e to the 4 pi. It's just two numbers. So this is the square root of 2, and this is the other square root. Right, now it's a matter of squaring this, or rather integrating this. Let's just simplify this. This is integral from square root of 2 to the other square root. This is u squared over u squared minus 1, integrated with respect to u. Whenever you're integrating a rational function, that means a polynomial divided by a polynomial, if you can, divide the bottom into the top, and then write the rest as a partial fraction. Well, one way of doing this is you can, instead of doing long division, dividing the bottom by the top, you can subtract 1 and add 1 at the top. So this is just a little trick. This is square root of 2, the other square root. This is u squared minus 1 plus 1. I'm just adding 1, subtracting 1 at the top, and then I'm going to split it into two fractions. So this is going to be u squared minus 1 over u squared minus 1 plus 1 over u squared minus 1, integrated with respect to u. This one is just equal to 1, and this one we're going to use, we'll factorize the bottom. So u minus 1 is written as u plus 1, u minus 1, and you write it as partial fractions. So here you'll use partial fractions. I'll do this up to some point. Right. So therefore, the length that we need to calculate is equal to the integral from the square root of 2 to the other square root, that large number, of 1 plus 1 over u squared minus 1, integrated with respect to u. The first one is straightforward. This is just equal to u. And if you write 1 over u squared minus 1 as partial fractions, that means write u squared minus 1 as u minus 1, u plus 1, without getting into much detail. This will become 1 over 2 into u minus 1. That's the second integral. Minus 1 over 2 into u plus 1. The second part will still have to be integrated with respect to u. So let me just indicate where these things are. There's a curly bracket there, and there's a curly bracket there, and of course for all of this there are limits. So here too, there's going to be a lower limit and an upper limit, like so. There's a lower limit of square root 2 and an upper limit, some nasty square root. So this is equal to this. Let's leave this as u to be evaluated between square root 2 and the other square root. Right? Take half out, integrate the respective functions. Right, so this is plus a half into. If you integrate 1 over u minus 1, you get ln of u minus 1. you integrate 1 over u plus 1, you get the ln of u plus 1 mod, of course, and eventually you'll put in square root of 2 and an upper square root. I don't think there's much to do here. This is now equal to this upper square root, whatever that square root is, minus root 2. So this is putting u equal to the upper square root and u equal the lower square root, plus half, and I think you can eventually evaluate that. We will now do one more example on determining the length of curves using the complex version of a curve. That'll be the next class. Let's stop here for now. Okay, in this example, we have a slightly different case. We're not dealing with vectors, but rather we're dealing with a complex plane. Recall we mentioned in class that every point on the complex plane is in fact a complex number. So that a curve on the complex plane represents a set of complex numbers joined by some curve using a parameter t. So in this case, of course, what we're looking at is, here's your complex plane, where the horizontal axis is the real part of your complex number, and the vertical axis is the imaginary part of your complex number. And every point there, of course, is a complex number. So if you take a curve on this complex plane, remember, it's a connection between various points. And a tangent to that is given by the derivative of the complex z. So if, in this example, if z is equal to, as a function of t, the parameter t squared e to the I pi t, then this curve will be obtained by taking various values of t. So t equal to 0, for example, will give you the point 0, that's the origin, and so on and so on. So and then z dot would be the tangent to this curve at some point with value t. So z here will represent, as before, the tangent as far as z is concerned. Okay, so suppose we want, so here's the example on this curve. What we want, right? Let's do this a bit better. What we want is the length of the arc, want the arc length between 2 points on this curve, z equal to t squared e to the I pi t. So we want the arc length between 2 points, and remember 2 points means between two complex numbers, between points, and this is in terms of z. This is z equal to 0 and z equal to minus 1, complex numbers. When we do the integration, we need this in terms of t. Otherwise, we cannot do the integration. Right. So the length is going to be given by, as always, the integral between two t values. I'm going to call this t equal to alpha and t equal to beta, and that's going to be the mod of z dot. So it's very similar to before, but we don't have vectors, we have complex numbers. There's no vector notation here. This is your z differentiated with respect to t. Take the mod of it, and this modulus that you're taking here is not the length of a vector, it is the mod of a complex number. So this is the mod of z dot integrated with respect to t between alpha and beta. Okay, we need to compute z dot and then the mod of z dot in this case. Right, first of all then, the function z dot is a derivative of z with respect to t. That's going to be your standard product rule. So z dot, first of all, is equal to, using your normal product rule, differentiate t squared, you get 2t. Leave e to the I pi t, that's e to the I pi t, plus t squared, and then the derivative of e to the I pi t is e to the I pi t multiplied by the derivative of the index. That gives you I times pi. Let's simplify all of this. You can remove e to the I pi t as a factor, so this is e to the I pi t into, well, what you got from the first term is 2t, and from the second term, if you remove e to the I pi t, you get I pi t squared. It's I pi t squared. So this is your z dot. We may simplify it further. You can remove t if you want, but we'll do that a bit later. What we're going to do from this is take the mod of the z dot, the mod of this thing, and integrate it with respect to t. But remember, the mod of z dot here means the mod in terms of complex. So therefore, the mod of z dot is going to be the mod of the e to the I pi t. So that's the mod of e to the I pi t in the complex sense. And then it's going to be the mod of this curly bracket. So it's a mod of 2t plus I pi t squared. The mod of e to the I theta is always equal to 1. E to the I theta. As long as the index is I theta, I, emphasis on I, the mod of e to the I theta is equal to 1. So this is always equal to 1. It's multiplied by the mod of this complex number, which is a plus ib. And you know that the mod of the complex number a plus ib is the square root of a squared plus b squared. But before we do that, we can remove t as a common factor. So this is the mod of t multiplied by the mod of 2 plus I pi t. So it's the product of two complex numbers. So this is the mod of t, and this is the square root of, square the 2, you get 4, square the pi t, you get pi squared t squared. And then it's a square root of all of that. That's the mod of z dot. We integrate this between alpha and beta. Alpha and beta has to be computed. Alpha is the t value that comes from the initial point z equal to 0, and beta is the t value that gives rise to the z point minus 1. So z equal to 0, that's the initial point, implies, and you can easily check this, that t equals, t equals 0. Substitute this back into z. And z equal minus 1, if you go back to the function z, this comes from t equal to pi. Or rather t equal to 1. You can check this. Substitute t equal to 0 for z. In z, you get z equal 0. Substitute t equal to 1 above, you get z equal to minus 1. In fact, you could get t equal to plus or minus 1 in the second case, but I'll choose plus 1. So I should say here technically z equal to minus 1 gives t equal to plus or minus 1, and we choose the plus 1. Right, now to compute the length of that curve. So therefore, the length of the curve, as we had before, was between alpha and beta, where alpha is now 0 and beta is equal to 1. We're integrating the mod of r dot, and because t is between 0 and 1, all is positive, so this is, the mod t is just t multiplied by the square root of 4 plus pi squared t squared, and all that integrated with respect to t. And this is a simple first year integration by simple substitution, right? So in this substitution, let's do the substitution slightly like so. You put, or you let u equal to the thing under the integration, under the square root. So put u equal to 4 plus pi squared t squared. Therefore, du is going to be equal to, differentiate the right hand side with respect to t, you get 2 pi squared t dt. So therefore, t dt is going to be 2 pi squared. On the one side, well, divide both sides by 2 pi squared. So du over 2 pi squared is going to be t dt. Well, you're changing the variable, so you're changing the limits also. T equals 0 implies that u is equal to 4, and t equals 1 implies u equal 4 plus pi squared. Put all of this into the length, so therefore the length will now be equal to an integral from, instead of 0 to 1, it's going to be from 4 to 4 plus pi squared. 4 plus pi squared. The integration, the t dt is going to be du over 2 pi squared, and the thing under the square root is going to be very simply u. So this is the square root of u du divided by 2 pi squared. That's equal to, take out the 1 over 2, this is 1 over 2 pi squared. You integrate u to the half. U to the half is u to the 3 halves over 3 halves. And you're going to integrate that between 4 and 4 plus pi squared, etc.